Hello everybody. It is my pleasure to introduce our speaker for this session, Dr. Konrad Kolesko. Konrad Kolesko is Polish mathematician whose research was probability theory, harmonic analysis, functional analysis, and random recursions. He is based at the Mathematical Institute of the University of Wrocław, Poland. He earned his PhD in 2012 from the University of Wrocław with a thesis on the asymptotic behavior of invariant measures of stochastic recursions under the supervision of Professor Dariusz Brykowski. Over the years, he has held a postdoctoral position at the University of Warsaw and has been actively involved in both teaching and research at the Wrocław, giving lectures in measure theory, probability, and related fields. Dr. Kolesko's current research interests include iterated random functions and branching processes, harmonic analysis, functional analysis, affine recursion, and fixed point problems in multivariate stochastic transformation. He has published several papers, often in collaboration with Professor Brykowski, Latala, and Mantimeir on crucial cases of smoothing transforms, tail behaviors of invariant measures, moment estimation for causes, and random walks on affine groups. We are honored to have him share with us his recent work today. Please join me in welcoming Dr. Konrad Kolesko, and please, you can start.
First of all, thank you for such a nice introduction. I'm really pleased to be, I'm an honor to have the opportunity to give a talk on such a nice webinar. The talk, my talk is based on a joint work with Ecaterina Sava-Huss from Innsbruck University. And so let me start with the model. The work. Okay, so we consider a two-urn model. So it's a model that consists of two urns. It's the urn A and the urn B. And then we also have a rule of how we replace ball. So whenever we see a blue ball with probability 1, we replace it by two blue ball and one white ball, and with probability 1/2 just by two white ball. And on the other hand, if we see a white ball, we replace it by with probability, say, 3/4 by two white ball and two blue balls, and with 1/4 by we do not add any ball. So how does it work? So at the beginning, we start, we are given one ball in one urn. So we pick the ball because there is no other option. And then we follow the first rule because it's the blue one. So it happens that with probability 1, we add now two blue ball and one white ball to the urn B. Okay, so now we are in the position where the when the urn A is empty, but the B is non-empty. So what do? We switch them. So
sorry.
Yes.
The drawn ball from urn A is returned to urn A or not?
No. So here, okay, I forgot to mention. So this ball goes so at the bottom. So here I will record the ball. So I put it here, and then the new balls are in the urn B. So now I replace the urn, and now the urn A is there are some balls in the urn A, and there are no balls in urn B. So what do we do? So now we pick by one ball from the urn A, and so suppose now it's this one is a blue. So now it happens that with this blue ball we flip a coin, and based on this we decide to add two white ball to the urn B, and the picked one ball goes to the bottom. So we put it here, and there are these two white balls. So we continue now. So suppose it happens that it's the white ball, and with three-quarter, probability three-quarter, we add this collection of balls, and the white ball end up here, and the blue ball goes, and so we take like these three balls, and it go here. So all the time the picked balls we put aside. So they are on the bottom here. And again, now the urn A is empty. We change we flip the urns, and we continue the game. So we pick a blue ball, add the balls to urn B. The next we pick one white ball. Then okay, it happens that that with this white ball, with probability 1/4, we add no balls. So now just we put this picked ball aside, and we add no new balls to the urn. So this is the rule that this is the model. So it's an example of a model that we are interested in, and what we are asking is now understand the behavior of the number of, say, some given color, the blue balls drawn up to time n, or you can say so it's the total number of the balls, the blue balls that are at the bottom, that are here at the bottom. So right now we have five blue balls, and this is after time so it's after time 9. So n of 9 is 5. So now it's more formally the description of the model. So each ball is marked by one color, which is a number from the set from 1 to j, and by the blue color I will denote what is the corresponding object on the example. So we have so in the example there was just two colors, and now for each eye, so for each color there is a probability measure on nj with 0. So it describes how many colors how many colors how many new balls we add to the system. So here, for example, we have if we pick one color, then then we have so with probability 1/2. With probability 1/2, we have the delta at the point 2, 1. So two ball of color 1 and one color of type 2. So two blue and one white. And with probability 1/2, 0 blue and 2 white. And similarly, so we have seen on the picture before. So if we pick the white color with probability 3/4, 3/4, we add 2 and 2 balls, so 2 blue, 2 white, and with probability 1/4, we add no ball. And balls are drawn from the urn marked by the A, so it's the urn A, and a picked ball of color I is replaced by an independent random collection. So it's a collection of numbers. So each number tells you how many numbers, how many balls of a given color is being placed to the other urn. So the Lij denotes here the balls of color J, and this is if we pick a ball of color I. And the new balls are added to the urn B. And when the urn A is empty, we replace it by the urn B. And as before, we would like to understand the number of balls balls of type I. Okay, and there is a typo among the first n balls drawn from urn E from urn A, and more precisely, we would like to understand the limit theorems for Ni of n. So this is goal of our research. Okay, so the first result is the strong law of large number, and so it turns out that the behavior the behavior of the object that we are interested in depends strongly on the spectral properties of the mean matrix. So it's the matrix whose coefficients are the expected number. For example, Aij is the expected number of balls of type J which are added to the urn B if we pick a ball of color I. So color and I so we can say about either by about colors or about type. So now we assume that A is primitive, so it means that some power, if you raise to some power, is positive matrix, and then you can use the Perron-Frobenius theorem, and so you concluded that there is some eigenvalue rho. And a unique eigenvalue rho and a unique eigenvector u, and if the rho is positive, then the process of the urns survives with positive probability, because as you might remember. There was a case when you pick a white ball, you add no balls. So it can happen that with positive probability, both urns are empty. But the point is that if rho is positive, then the process will survive and will not die out. There will be always some balls. And this is some classical result from branching processes. And so in the case of example, the matrix A is given in this form. So you can compute the spectral radius, which is it's larger than 1. So it will survive. And you can also compute so it's the eigenvalue, and you can compute the eigenvector. So all the coefficients are positive. And the theorem, so the first theorem says that if we have some x log x condition, then on average, so if you divide by n, the number of balls of a color I divided by n, so it's I recall that ni is the number of picked color of type I up to time n. It converges almost surely to some constant. The constant is explicit. And it's derived from the eigenvector, and so the limit exists almost surely on the set when there is no die out. When the process survived. And now it's the more challenging is what about the fluctuations? Because okay, you have some process converges to some constant, and you may ask what are the fluctuations? So if you subtract from the limit, do we get some kind of central limit theorem, or there are some other fluctuations. So this is our next theorem. So we arrange the eigenvalue of A in a decreasing order according to the modulus. And so there are some complex numbers. There are at most j of them, and so the first one is is the largest one is rho, and then the second one is the absolute value of the second one is strictly smaller. Than the rho. And by gamma, we denote all the eigenvalues whose absolute value is the same as the modulus of the second eigenvalues. And here is the theorem, which might looks a bit ugly, but okay. So let me explain it. So for the sake of simplicity, we assume that all the eigenvalues are simple. So there is just one dimensional eigenspace, and we assume that we have some bit more than just a second moment. So we have 2 plus delta moment. So then there are random variables x. So we have some random variable x, a function, and we also have a random variable x lambda. So for the lambda from the set capital lambda, and we also assume that we have such function f lambda such that those functions are continuous and one periodic. So they are continuous and one periodic. And now we have kind of trichotomy. So if the modulus is large enough, so it's between a row and square root of row, then okay, so this is the leading term, is the linear part, is the leading term, and then we have basically you can think that the fluctuations are of the order n to log rho of lambda 2. So this is the so this is how you can morally think that we have some fluctuations, but there are also there are some ugly terms. So there is some there is a kind of periodicity, and there are some limiting random variables x lambda. On the other hand, so there is no and in most of the cases the x lambdas are just some random variables, and they have nothing. There is no reason for them to be Gaussian. So there is no hope for any Gaussian fluctuations. So on the other hand, when the modulus of lambda 2 is on the kind of critical circle, so the circle of radius square root of rho, then we have some kind of CLT. So the point is that if we subtract the leading term and we divide by n times some logarithmic term also, n times log n, square root of n log n, and also we have this kind of continuous function. So you can think of that there is some kind of fluctuation of the variance. So it converges to normal distribution. And if the second eigenvalue, the absolute the modulus of the second eigenvalue is inside this is sufficiently small, so it's smaller than square root of rho, then we have similar result, but without this logarithmic correction. So this is a kind of trichotomy that we prove for the Earn model, and the kind of trichotomy appears in many places already in many places in different models which are somehow connected to branching processes. So that's that's why we were interested in this kind of problem. So let me now compare our model to the one Earn model. So in one Earn model, there is just one Earn. So if you pick a ball, you have some replacement rule according to the color. And if you you draw a new collection of a ball, but in this model it's quite common. It's to return the picked ball to the urn together with the new collection. So it is with replacement. And so so in this model, the spectral radius of the matrix A. So the matrix A is it's the matrix whose coefficients are the expectations of the number of balls of type J if you pick a ball of type I. And so here in this process, because you do not remove, it will you will always have balls. So there is no need to assume that the spectral radius is greater than 1. But there are so in this model there are also this kind of trichotomy. There are free fluctuations regime. So the conditions differs, and so here what is important, so the lambda 2 is not the largest according to the modulus, but according to the real part. So we order the eigenvalues according to the real part, and lambda 2 is it is the second after the spectral radius rho. So there are three parts. There is the kind of trichotomy. So if the real part is large enough, then the fluctuations are some kind of polynomial. So it's n to a power. The power here is smaller than is something between 1/2 and 1. Yes, this is the power of the n. So and in our case it was kind of you take the logarithm of lambda 2 divide by the logarithm of rho. So it's a bit different index and then a bit different exponent. So if the real part is on the critical line, so the critical line is where the so it's if lambda is on the critical line, so it means that the real part is equal to rho over 2. Then the fluctuations are of the order square root of the linear term n, and kind of logarithmic correction, and with Gaussian limit. So it's very similar to our result. And if the real part of lambda 2 is strictly smaller than the rho over 2, then the fluctuations are of the order square root of n with with a Gaussian limit. So without there are no logarithmic correction. And this is a result by Svante Jansson from 2004. And so let me first give some rough idea how you can prove this kind of result for the one urn model. So one of the basic tools is the embedding. So you can embed the whole process. It's called the Atreya-Karling embedding into continuous time Markov branching process. So the birth, each birth corresponds to adding balls to urn. So what do you have here? You have a branching process. So So there are individuals, say, of the color of type or color blue and white. Each ball has an exponential clock. When it rings, the balls it corresponds to the event that the ball is picked. So when it rings, the balls give birth to a new collection of balls, and so this is the kind of continuous time Markov branching process, and and so for xi, the number of individual of type I in the continuous time Markov branching process, the leading term, there are some classical results, and then the leading term is some constant a times e to rho t times some random variable w. It's a mean 0, 1, and this w does not depend on I. So it's some universal random variable, and so this is the leading term. But then you can look what are the you can ask about the fluctuations of the balls of type I in in this branching process. So the next term is either of a similar form as the first one. So it's the some constants b times e to lambda 2 times t times some another random variable, or it is Gaussian, and the variance is either of this form, like we have here, or there is some additional correction, polynomial correction. And so the fluctuations, which fluctuation do we take, depends between the relation of the real part of lambda 2 and the number rho. So it's exactly the kind of conditions that appeared in the on the previous slide, and similar fluctuations, but with different constant, holds for the total number of individuals. So you can ask how many individuals are after time t. So this is the xt, and then you can ask what are the fluctuations, and it's one of these three, depending depending whether the e to lambda 2 of t is greater than the square root of e to rho t. But okay, so there are some results, and so what Jansson did was he proved this kind of limit theorem. He proved that it can be lifted to the Skorokhod space. So he derived the functional limit theorem, which then allowed to go back, and so we take the composition. So you can then stop at time when the total number is equal to n. So this is the time x to minus 1, so x inverse. So the inverse function of x evaluated of n. So it's the time when there is n balls in total, and at that time we calculate then how many balls are of a given type I. So having a limit theorem functional limit theorem for x and xi, you can derive the limit theorem for the ni. Okay, so this is how it works for the one earn model. And now is the question: how we can we use a similar approach to our two earn models? And the answer is yes, but it's a bit more complicated. So first of all, you can convince yourself that it's not so difficult to see that if you if one if say the first if one urn is empty, so say the first one is empty, or say the second is empty, then the collection so when the all balls are in one given urn, then this process is just a multi-type Galton-Watson process. So it's a branching process which where you go from one generation to the other generations. So you go yes. And so now so this is our the balls which we put aside. They form a sum of like the first n generation of Galton-Watson process. And now is the question how we can interpolate between, because we would like to have we would like to have continuous time as before. So how do? We need to somehow interpolate between the integer times, and in order to do this, we mark each individual u, so it's the individual in the Galton-Watson process. It's marked independently of everything else by some uniformly distributed random variable on the interval 0, 1. And now we have kind of threshold. So so for any x, so if we fix some threshold by Zn of Znx, we we consider all the balls whose generation is smaller than n, or if it's equal to n plus 1, it can be equal to n plus 1, but the ux has to be smaller than x. So this kind of this u of u and they tell us what is the order of the balls, and we can do we can define a similar process, but with a condition that u is of type J. And now we have a continuous time process yt and yjt is we take the integer part and the fractional part of t. So we have we can encode so we can embed our process in this kind of processes. And why is so? Why we are happy with this is that this is because both the Znx and the Znxj they are a type of a CMJ process. It's a Courant-Mode-Yargar's process. So what it is? It is a process of the following type. It's a sum of all the the individual u which are ever born, then we have some random function psi of u, and here we have u minus n, which so you can think of the h of u at time n. So if u is born at time n, the h is equal to 0. It can be also negative, and is a function of type. And why does it help us? Because we have some limit theorem for this kind of processes. So in a previous work with Ecaterina Sava-Huss, we were able to obtain a CLT for this multi-type CMJ process, and roughly speaking, we have some leading terms. The leading terms. When the so here is the condition on the spectral on the eigenvalues that are so there are some the eigenvalues. So we sum over all eigenvalues which are large enough. There is a constant which depends on lambda and depends on the function psi, and w of lambda denotes some complex random variable which depends only on lambda, and here we have the lambda to power n, and we have some fluctuations. So these are the fluctuations. They are roughly of the leading term as the leading term, square root of the leading term times some Gaussian. But roughly is that we have some function L of n here, and the function is equal n if there is some root on the critical. So if there is some eigenvalue on the critical circle. So otherwise it's equal to n, and we can okay. So this is a kind of theorem that we have for this kind of processes, and now we automatically also get the finite dimensional distribution limit theorem, because we can use the Cramer-Wald device, and because here the functions are the family of such functions, that these functions are called characteristics, are closed under say linear combinations. So we automatically will get the functional finite dimensional distribution, convergence in finite dimensional distribution. But the higher moment allow us to conclude to lift the convergence to the Skorokhod space, and finally we can then conclude as before the limit theorem for the process that we are interested in. Okay, I think that's all I can. Yes, so thank you for your attention.
Thank you, Dr. Konrad, for this nice talk. Are there some questions, please?
Yes, I have a question.
Yes, please.
What will be the smallest model for which you don't know the limit laws?
You mean for which you don't know The W,
Yes, so there are always many possibilities of variations, more urns, more colors, different types of picking, adding. There is always a lot of different variants which are possible. And what is the smallest, the simplest model for which the limit law is not known?
um, okay, so you are talking now about the model, the kind of two-error model that I was presenting, or not?
Yes, let's say the simplest generalization of your model or variants of your model for which you don't know the limit law.
Okay, so for which I don't know, so I can say for any other generalization I don't know. Um, so 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 I have to admit I'm not an expert in Earn models. I work on mostly in branching on branching processes. So that uh, um, so 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 so. So the point was that that with Ekaterina we proved limit theorem for this Grand Modiargas processes, and we were looking for some nice application, and then we came up with this model. But now it's like you are asking about model which we cannot apply our method. Yes. Um,
Yes, or perhaps to which it was not yet applied, because who
yeah,
knows if it can be applied or not.
so I can say that it is only so far it's only applied to this model. So we haven't tried any other generalization. So I can say that any other generalization, I don't know the limit theorem for any other generalization.
And to which level of precisions do you have some insight on the sigma and the f lambda functions, the periodic ones? There are Fourier series for which you
No,
exactly
no.
know the coefficients.
You are asking about this function, yes? Here, they are explicit function, but they are nasty. So you can compute them explicitly. You can yes, you can compute the function the function f and sigma explicitly. The limit theorems here, the random variables here, x and x lambda, they are obtained by martingale methods. So you only know that there is some limiting random variable, but we do not have any clue about what is the law of of those random variables. So we have no information about this. So it's usually in this in this branching processes only some only for some concrete models you are able to determine the distribution, but in most of the cases you just know that there is some random variables like in the Biggin's theorem or Kessen-Stigum theorem. You only know that there is a random variable, and you can ask, then you can you can you can you can try to to uh, to prove some properties, but the explicit formula for the distribution is rather hopeless in
Okay,
general.
so here f lambda and all the quantities are very precise.
Yeah.
Just x and x lambda are kind of
Yes.
they exist, but we don't know much
They
more.
exist. Yes, and comes from this kind of martingale's method.
Hmm? Okay, thank you.
And in this theorem, the distinction of the three cases, the change of phases,
Yes.
are obtained via martingale techniques or something else.
Um, yeah. Okay. Some. The point is that. Um, this kind of phase transition is due to the asymptotic of the branching processes. So in the branching processes, it's usually you have the leading term, and then you look what is the subleading term, whether the subleading term. Okay, maybe I will go to the last slide. So for example, here there is the leading term is for lambda equal to rho, and then you have different lambdas. They are subleading. So the point is that you can construct you can get this, you can obtain this using martingale methods, and the point is that all these terms can be written again in this kind of form, so there is a way that you can decrease decrease the you can decrease the fluctuation of quantity of such type, but you can do it only when the eigenvalues are sufficiently large. If they are small enough, there is no problem. You can center with the mean, not with such something random, but with the mean. The only problem is when there is eigenvalue on the critical circle, and that's why there is this function L. So it somehow tells you that the variance explode. It's explode faster than the row of n. So that's the idea of the proof. And here you can see that if the second if rho is smaller than square root, if the lambda, if all the other lambda is smaller than the absolute value of lambda is smaller than square root of rho, you have fluctuations of magnitude smaller than square root of square root. Yeah, so the point is that the Gaussian fluctuations are greater.
Okay.
So you don't see. So you only see the terms which are higher than the Gaussian fluctuations.
Okay. So in your work here, you have only two urns.
Yes.
And you continue to draw from urn A up to urn A becomes
yes
empty. And in this case, you go to urn B and so on. And
yes.
if you have three urns, A, B, C,
yes,
and you continue to with urn A, you add to urn B up to urn A becomes empty. And after you go to urn B, you draw from urn B, you put in urn C, up to urn B becomes empty, and after C, A, and so on. This circle.
Yes. So probably it doesn't change anything. Yes, because you can for example, you can forget about the ABC. You have one urn, the other urn, and go. If it's empty, you move to the that is non-empty and continue. Yes, so it seems that it's exactly the same process.
You mean that we combine together B and C?
Yes. So here I don't see why it should be different.
The probability of picking won't be the same.
Not
if
the
you
same.
merge the urns, the probability to pick each color won't be the same. I'm not so sure about uh, merging together some urns will be the same evolution?
Okay. So probably don't understood. So you are saying that you want to merge the urn then?
No, no. I understood that you were answering that, oh, we could merge the remaining urns, and therefore it should be three urns should be the same as two
Yeah.
urns.
Yes. Yes.
I understood that it
Yeah.
was your reasoning. And I was saying that, but then I am not so sure because then the proportion of the urns and therefore the probability of picking the colors is not the same. So for me, I am not sure that the processes are isomorphic if you do this trick. At least I don't see it.
Um. So you put so from A you put to B, and from B you put to C, and from C you put to A. Yes.
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 And I am not that sure that it is equivalent to a model with just two urns.
Sure.
I
I'm
think
not
the order of the colors which are drawn will be the same, but the branching process will be more like taking two steps at once. If you only look at when you put all the balls in A, then you basically took two steps there because once you generated B from A, you generated C from B. That's like two branching events. But the order you draw them in doesn't depend on which urn they are in, only the number of balls that are in each urn, right? So
So, Daniel, you are saying that what you want to do is you want to do 1%, one urn once and then the other merge urn twice. This is what you are saying?
So the way I understood this is that you start with A. There are some balls in A, then you generate some balls in B, and then A is empty at this point. This is like a one branching step.
Yes. Yes.
If you add a C urn as well, then B also generates some balls in C. That's also another branching step. And then you put all the balls in C into A to basically start again. But this is like if you generated in B, then put the balls in A, generated in B again. This is the same distribution as if what B would have generated in C, and then put them back in A again. So this would be if you look at just the number of balls in A as a process, then this will be the same as before, just taking two steps instead of one. But if you record the order of the balls drawn, then the distribution shouldn't change because it only
Yes.
depends on the number in the urns.
And in your process, Konrad, you were always adding the urns, the balls to the same urns, not in two different urns? You were never doing this?
So I was adding so if you go to the beginning, uh, picking from the urn B, and you always put to urn B. Always, then you will just flip the urns from A and put to B. Always from one urn to the other.
Okay, there is no type of multiset or whatever. Okay.
Yeah.
Other questions, please?
Yes, I firstly have another question.
Yes.
Did you consider to try to solve the model, the exact distribution at time n? Not the asymptotics, but the finite time distribution, and to get a generating function for all of this. Is it a solvable model?
Wow. The point is that like if you remember the embedding, it's already quite nasty. Um, contrary to the one urn model, there is no Markovianity. It's so all these kind of if you'd like to get some some nice equation, I think it's hopeless here. It's because you know what is in the integer time, and then you would like to somehow uh, interpolate in the time in between. So it's really nasty and yes. So uh,
But for the discrete time process, you don't have any interpolation. This is more
it's the
for your approach for the limit, which needs this interpolation.
sorry.
You don't need this interpolation for the discrete time process.
Okay, so now I was saying about the embedding, but yes, for the process itself, you don't need interpolation.
So
So
another way to rephrase my question is, do you know if there is a PDE, which is a modelization of the process in discrete time? You know this approach? This is the one which is used, for example, by Flageolet and so on their earned models stuff, where they use generating functions, and then after you can get the limit laws.
yeah, so it's the PDE. It's basically for the PDE you need kind of Markovianity, yes.
It is helping a lot, I agree.
Yeah, so that was my kind of maybe not precise reasoning, but I've kind of I think that this is the reason that in this model, in one model, you have this kind of Markovianity, so you get some PDE, and it really helps. But in our
Yes,
model,
and
it's
swapping the earns and so on is not so easy to handle. To handle the
yeah,
earns, enfin, the emptiness also is not that easy to handle. So there is a lot of obstacle
yes, and
to solve it in an exact way. But the model is nice, so I could trust that maybe there is something nice to find also in
yeah,
discrete time.
for example, here the fluctuation where the function let me like the function here this kind of log rho n minus x
Mhm.
so you can think of that that this is a kind of variance, but it this tells you how whether you are about to flip the whether you are about to flip the urn, or you are in balance. So the if you are at the time uh, when uh, when the number of balls in both urns are large, so it's different variance than at the time when in one urn there is only few balls, and all the other are in this in the second one. So
Yeah.
so
And with respect to this theorem, here I have another question. Quite often for earned models, there is a kind of trichotomy with respect to the largest eigenvalue to its position to one half. It's or
yes.
and can you give an intuition of why one half here becomes square root of rho
Yeah,
and lambda two?
okay, so then the intuition is that in the one earn model, now if you look at the Carlin embedding, so in this branching continuous time branching process, if you look what is the so if you ask what is the total number the expected number at time t, it is the E to T times A matrix. Yes, this is the semi-group this is the semi-group. Uh, this is the semi-group which describes you the evolution of the urns in expectation. But in our model, in expectation, it is like in the Galton-Watson process is A to power n. that's why it's different. Here is the exponent, and we have just a power, the nth power, or the t power, if t is integer. And here is and in a one-Earn model, it's the e to t times a. So that's the reason that here in our case we have the log, but there are no log in the one-Earn model. You are muted.
I was saying, yeah.
Other questions? If not, we have to thank again Dr. Konrad Kolesko for this nice talk.
Thank you for this feedbacks. It was really nice to discuss this topic.
And see you after 2 weeks with Bizdani Daniel, who will speak us about three-type Galton-Watson process with immigration. See you 29 October. Bye.
Yeah. Bye.
Thank you for the talk. Goodbye.
Thank you.